This is a video for AQA Mechanics, Circular Motion Section 2.5, where we're looking at the motion in a vertical circle. Well, we know that in examples that we've looked at previously that we've normally not considered forces such as friction or air resistance, which would create a loss of energy and therefore the angular speed wouldn't be constant. There are other situations where the speed can vary, and one of these is the idea of a vertical circle where the weight of the object needs to be taken into account, as this produces a force which gives us an acceleration around the circle itself in the direction of the circle. So we know that we've got our value of V is equal to R theta dot, or R omega, and if we have a variable angular speed V, then there must be an acceleration in the direction of V. So we produce an extra acceleration, as well as the centripetal acceleration towards the center of the circle. Then there is a tangential one, which is R theta double dot. So here we've got two accelerations, one of which is producing the circular motion itself, R theta dot squared or R omega squared, and then we've got another acceleration which is tangential. That one we're not going to be considering in the calculations. However, we will be looking at how we can calculate the way that the speed changes. So an example of that, let's consider this situation where we've got a mass of 2 kilograms at the end of a light rod. So the light just means that we don't have to worry about the mass of the rod, which is of length 0.9 meters. So we could add that into our diagram to say that the radius here is 0.9. And the particle is then moving in the circle because the rod is attached to O, so it's hinged here, so it can drop downwards. Initially it's starting at rest, and what we want to know is what's the speed when it reaches B here at the bottom. So we want to calculate V at the bottom, given the fact that at the start it's starting from rest. At first sight you might think this is quite a complex situation because we've got a tension in the rod here. However, that tension is not moving, so there's no displacement taking place in the direction of that force. So we have a situation where there are no external forces, and therefore we can use energy considerations to solve this. So at the start here we have kinetic energy is equal to 0, and we have potential energy given by mgh, where h is just the radius of the circle, so the potential energy is mg multiplied by the value 0.9. And at the bottom we have potential energy equal to 0 relative to the starting point, and therefore that potential has been converted into kinetic energy, a half mv squared. So the conservation of energy then tells us that we have that 0 plus mg multiplied by 0.9 is equal to 1/2 mv squared plus 0, and therefore v squared is equal to 2 mg, sorry, beg your pardon, the m's cancel out from that equation, so it's equal to 2g multiplied by 0.9, that's 1.8 g, and v is therefore equal to the square root of that, which is equal to 4.2 meters per second. there it is written out neatly. The second part of the question is going to ask us to find the tension in the rod when we've got to this position here. So there's going to be a tension acting towards the centre of the circle. So we're asked to find the tension in the rod when we're at B, knowing that the value of V here is equal to 4.2 meters per second. So we've got forces T and mg acting downwards, producing our acceleration towards the centre here. So the centripetal force is equal to mv squared over r. Once we've got our forces on the diagram, we can resolve vertically, so that T minus mg must be equal to the centripetal force mv squared over r, so that T is equal to mv squared over r plus mg. We could use our value of V that we found in the last part of the question, but we had an expression for V squared. V squared was equal to 1.8g, so 1.8 multiplied by 9.8, and therefore T must be equal to mv squared, that's 2 multiplied by 1.8 multiplied by 9.8 divided by the value of r, which is equal to 0.9, and then plus the mass 2 multiplied by 9.8. And if you calculate that, T turns out to be 58.8 newtons. So the tension 58.8. That's the end of this video. In the next one, 2.6, we'll be looking at when circular motion breaks down.